Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at the 2019 AP Calculus exam, specifically looking at some of the free response questions. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight I'm excited to be joined by our two panelists, Vickie Carter and Steve Kokoska. Vickie's been teaching high school math for 44 years at West Florence High School. She's a former co-chair of the AP Calculus Development Committee and served as an exam leader at the AP Calculus reading in the summer of 2018 and 19. She received the T-Cube Leadership Award in 2015, and Vickie has served on TI-Nspire authoring teams and has presented at many national, state, and local conferences. Vickie, it's great to have you with us.
Thank you. It's a pleasure to be with everyone tonight.
And Steve is a professor in the Department of Mathematical and Digital Sciences Department at Bloomsburg University. He is a former chief reader for the AP Calculus reading and a member of the Development Committee. Steve's an active T-Cube instructor and College Board consultant with recent workshops in China and Singapore. He just published an AP Calculus text and the third edition of his introductory statistics text. Steve, it's great to have you with us tonight.
Thank you very much, Mike. I'm delighted to be here.
We're expecting a large crowd, so your audio is muted. Feel free to send questions to Steve or Vickie using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate from the very top of the WebEx menu and choose Audio Broadcast. At this point, Steve is going to discuss our agenda.
Thanks, Mike. Well, we've already done the welcome and introductions. I'm going to start out and talk about the 2019 free response question 82. I'll do a quick question review, and then I'm going to talk about the scoring guidelines. The way that I like to think about this is I'm going to give everyone a brief briefing. Then I'm going to pass the screen over to Vickie, and she's going to talk a little bit about technology strategies, how you would use both the TI-84 and the TI-Nspire to not only solve some of these problems, but to visualize, justify some of the results. And at the very end, I'm going to show or demonstrate or add a couple of problem extensions. These are problems that are related to AB2, but may ask your students to think a little bit more, build upon some of the information that's given in AB2. And then I guess at the very end of this, Michael, we'll have a webinar drawing.
Thanks so much, Steve. Yeah, stick around to the end because one lucky winner is going to receive a T-Cubed International Conference registration. And Vickie is going to discuss our expected outcomes.
Okay, everyone. Well, hopefully you'll have a little better understanding of the scoring guidelines as Steve goes through those. We are, as he said, going to demonstrate some technology with both the TI-84 and the TI-Nspire, especially demonstrate what the students need to be able to do to solve the, I think it's part C and D is where we would use most of our technology on this AB2, but also to look a little bit at some explorations that we could do. And then, of course, we have the problem extensions that we want to share with you.
Thanks so much, Vickie. Steve, you should have control. Feel free to share your screen.
Whoops. All right, let's see if I can do that.
And while Steve is getting ready to share his screen, in case you want to make your screen at home a little bit larger, right now your screen probably shows the left side is Steve's desktop that he's sharing. The right side might be like the chat window or Q&A window, things like that. If you want to maximize the view that Steve's trying to share, there should be an icon near the top of your screen. And if you click that icon, it will sort of split up into three different icons. It looks like a view icon. And the icon, if you want to maximize things, looks like a rectangle with two other small arrows coming off the top right. Thanks so much, Steve.
Okay. All right, on the left-hand side of the screen is the statement of the question. I'm going to leave that up there for a while to make it easy to reference back. On the right-hand side of my screen are my slides or my slide deck, and so I'll be going through or changing the right-hand side. So here's a quick outline of what I'd like to talk about tonight in relationship to the scoring of 82. I'm going to start by taking a quick look at the pre-response question and then the scoring guidelines that were used at the AP Calculus reading actually in Kansas City. And I'm going to give a brief summary of student performance on this question. And obviously, this isn't something that you get at the reading, but Vickie and I have access to the question leader reports. And so I've sort of summarized this into a student performance slide or two. Then I'm going to consider more detailed interpretations of the scoring guidelines, how these guidelines were applied, I think, in certain situations. And where possible, I'll look at some common student errors. And where appropriate, I'll show you some specific scoring examples, that is, examples of student writing responses and how that was scored. So let's start by looking at the question. And just a reminder, as we begin looking at AB2, this was a calculator active problem. So that means that students may be required to use their calculator in only some of the parts of this problem or all of the parts of this problem. Sometimes that's a common misconception, that if it's a calculator active problem, you must have to use your calculator in every single part, and that's not necessarily true. So in this problem, the velocity of a particle p is given by a differentiable function v sub p, and we have selected values of v sub p of t are given in this table. And we know that the particle p is at the origin at time t equals 0. In part A, we need to justify why there must be at least one time t in this interval, 0.3 to 2.8, with the acceleration of the particle p is 0. And in part B, we're asked to use a trapezoidal sum to approximate this definite interval. In part C, we get a second particle q introduced, and it moves along the x-axis with velocity given by a new function v sub q. And we need to find a time interval during which the velocity of this particle is at least 60 meters per hour. And then we need to find the distance traveled by particle q over this time interval. Holy Toledo. And then in part D, we're given the position of particle q at time t equals 0. And we need to use the information from part B. So we need to bring in the information, our answer from part B. And we need to use this function v sub q to approximate the distance between the two particles at time t equal 2.8. All right, so here we go. Here's the scoring standard. I'm not going to read through everything here, but let's take a look at how the points, the 9 points, were distributed. So part A was worth 2 points, and 1 point was for conveying that difference over here on the left-hand side, that this difference is equal to 0. And 1 point for presenting a sufficient justification using the mean value theorem. Now, you'll note that there is an alternative solution given on the scoring guidelines. This isn't too common, but when we look at student papers and we see that students are indeed solving a problem in 2 different ways, we may see 2 different scoring solutions here. And this second common solution presented by students involves the extreme value theorem. Now, I happen to think that this was a little bit tougher to do, but there were enough students who were solving it this way that it ended up on the standard. And part B was worth simply 1 point for the answer using the trapezoidal sum and for conveying that the student was using the trapezoidal sum. Part C was worth 3 points, 1 point for producing a correct interval. Notice that word interval is used over here. 1 point for writing a correct definite interval that can be used to find the distance traveled by the particle q. So we want to see this definite interval. And 1 point for the distance traveled by the particle q. So here it is, 106.109, rounded or truncated, 106.108. And finally, part D was worth 3 points. The first point was for writing a correct definite integral that can be used to find the distance traveled by particle q over the interval 0 to 2.8. So let's see, that's this definite integral right here. The second point was for finding the position of particle q at time t equals 2.8. That's this answer right here. Let me just stop for a second and make a note. This is a little unusual in that this position was not asked for in the problem, yet the student had to produce this answer. It's an intermediate result, but the student had to produce this to earn the second point. And then finally, the third point was for the answer, that is the distance apart for these two particles. So here's a little bit about student performance, some general comments about student performance on this question. So up here in part A, many students did recognize that they needed to use the mean value theorem. However, some made errors in communicating the hypothesis or simply didn't state the theorem hypothesis. Some students failed to present the relevant difference quotient needed here. And of those students who did present a difference quotient, unfortunately, there were some arithmetic errors. And some even presented the reciprocal of the correct quotient, so think about that difference quotient. And some students actually attempted to use the intermediate value theorem for justification, and that's simply not a valid approach here. Down at the bottom of this slide in part B, many students presented a correct trapezoidal approximation, and they actually had sufficient work here. That was pretty nice. However, there were some responses that lacked supporting work or with poor communication. And alas, there were some arithmetic errors here also. Kind of cool, maybe a little longer, but some students actually used an average of a left and a right Riemann sum approximation, and that's a valid approach. It's a little bit longer. I think it's prone or apt to produce a few more arithmetic errors, but some students did it and did it correctly. Okay, next slide. In part C, most students here did indeed present an appropriate interval with correct notation. So we were looking for some sort of correct interval notation. However, some students unfortunately listed only values for t. So evidently they went to their calculator, they used technology to find the points of intersection, but they did not present an interval. And unfortunately, some only found one point of intersection. It seems like many students understood the concept of distance traveled here, which is a good thing, that they needed to use a definite integral. However, there are still some decimal presentation errors here, and there were some intermediate rounding errors. Down towards the bottom of this slide in part D, many students presented a correct expression for the position of particle q. But there were several common errors, unfortunately. No use of the initial condition, for example, incorrect value for the position. That often could be linked to calculator usage. Often no value at all presented for the initial condition. And unfortunately, again, there were some decimal presentation errors. And finally, most students did recognize the need to find the difference in positions of particles P and Q. That's a good thing. So just a couple of reminders as we look more carefully here at the scoring guidelines. There were no units required in any part of this problem. So any units provided by the student this year were ignored. I can't guarantee that that will always happen, but that's what happened in 2019. And because this is a calculator active problem, there were decimal presentation errors possible. And we have a scoring rubric, we have a way to handle that. In addition to that, there was a trigonometric function involved here, and so there were degree errors possible. That means that students were solving this problem with their calculator in degree mode. Yikes. And we have a way to deal with that. So there were three common student responses in Part A. Let me just backtrack a little bit on that. The most common involved the mean value theorem. I think that's the way that I solved the problem, and I'm going to focus on that solution, in fact. The second involved the local argument and the extreme value theorem. I think that this is, in my opinion, this is a little bit more difficult argument, but we scored this by using the scoring guidelines. And finally, some students attempted to use the intermediate value theorem, and again, that's not a valid approach here, and the reason is because we don't know enough about the function v prime of p. We weren't given enough information about that function. So the first point in part A was conveying that the difference v sub p of 2.8 minus v sub p of 0.3 is equal to 0. So the general philosophy in awarding this point was, well, did the students sufficiently convey that difference, that v sub p of t is equal at those two values, 0.3 and 2.8? So here are some sample student responses and how each of these were scored. In examples 1 and 2, the student has certainly conveyed that v sub p of t is equal at these two values. So they earn the first point, and the E over here means that they're eligible for the second point. In example 3, the student has also conveyed that v sub p of t is equal to at the two values of t by presenting an applicable mean value theorem quotient. So that earns the first point. Now, example 4 is pretty minimal. Some of you are probably cringing here, but this also earns the first point. And let me just add, not in my class, but on the AP exam, the way that it was scored in 2019. In example 5 here, the student also earns the first point. Notice that they've earned it in words. In example 6, the student does not earn the first point. They must explicitly use the values of v sub p. They must use the table, go to the table, and draw those values. And in example 7, the student doesn't earn the first point, and the reason is because the word function is too ambiguous. We don't know what function the student is talking about. Okay, in part A, the second point was earned for the correct justification using the mean value theorem. And there was an eligibility criteria here. This often occurs in problems. So in order to be eligible to earn the second point, the student must earn the first point. So to earn the second point, the student response must explicitly declare that v sub p is continuous. They don't have to say that v sub p is differentiable. And some of you are probably thinking about this or even solved it this way. The student can certainly use Rolle's theorem, and the reason is that the value of the function is the same at the endpoints of the interval, so that was fine. And okay, they can even relabel or misspell v sub p of t here under the pressure of a high-stakes exam. For example, the student may state their justification using a function labeled just as v. So to earn the second point, the student must explicitly state that v sub p is continuous and connect v prime of p, v prime sub p of t to the first point. All right, here are a few more examples and how each was scored. In example 1, the student has misspelled v sub p, but they have indeed conveyed that v of t is equal at t equal 0.3 and t equal to 0.8. They stated that v sub t is continuous. They've used Rolle's theorem. This response earns both points. That's a 1-1. In example 2, this is another misspelling, and you know what? It's pretty minimal. It's right over that line, but it also earns both points. In example 3, the student has also misspelled v sub p, but they've sufficiently conveyed the equality. But notice in this response that they never said that f was continuous. So this earns 1-0. All right, in part B, the first point in part B was for the answer. Simply put, the sufficient evidence of the trapezoidal sum. During this point, the student must present correct values, of course, and they have to present evidence of a trapezoidal sum. That means we need to see at least 3 products, at least 3 terms, and a sum. Now, the student can earn this point with an implied sum. That means they don't have to actually put addition symbols. And they could also average, again, the left and the right Riemann sums. And we won't worry about symbols here like approximate and an equal sign. Both of them are okay in this case. So here's some quick examples for part B and how each was scored. In example 1, we see, let's see, 3 products, 3 terms, and a sum. And you know what? This is a final numerical answer, so it does not have to be simplified. So this earns the point. In example 2, the student has not sufficiently conveyed a trapezoidal sum. This does not earn the point. And examples 3 and 4 are essentially bald answers. There's no evidence of any kind of a sum, so neither one of these earns the point. All right, I hope I'm making good progress here, Michael. Here we are in part C. The first point here was for explicitly stating the correct interval. The interval presented can be open or closed. The interval may also be presented in exposition or in prose in writing out a paragraph or a sentence. If the interval is only evident as presented in a definite interval, then the first point is not earned. That means that we're not going to read the interval from the limits of integration. Here are some quick examples associated with the first point and how each was scored. The first 3 examples all earn the first point, eligible for the second and the third. I'm a little uneasy about examples 2 and 3 in my class, but again, under the pressure of a high-stakes exam, they earn the first point. In example 4, the student here has not presented an interval. They don't earn the first point, but they're still eligible for the second and the third. Similarly, in example 5, there's no interval presented. And in example 6, be careful here, the student has presented or has a decimal presentation error. They don't earn the first point, and they're inoculated or immunized against other decimal presentation errors only in this problem. So the second point in part C was presenting a definite interval that represents the distance traveled by this particle Q over the appropriate interval. So the student earns the points for any one of these 2 integrals for any values of t sub 0 and t sub 1 that satisfy this inequality. You don't need the absolute value symbol here because v sub q is positive over this interval, 0 to 4. Now, if the student omits the dt, they may still earn the point. It depends upon our interpretation of the integrand. And there are a few examples below here in this slide, which I'll get to in just a minute. So here are a couple of examples of expressions that earn the points right here in this line. All of these expressions satisfy what I stated up here in part 1. And let's see, here are some examples of mishandling of the constant 60 and or the dt. So here in this first one, the student earns the second point for appropriate values of t0 and t1. That means if they satisfy this inequality. But they're not eligible for the third point. And in the second example, the integrand expression is simply wrong. So the student doesn't earn the second point, and they're not eligible for the third. All right, the third point in part C was for the distance traveled by the particle Q. And we expect the student to use technology here, of course. I think Vickie's going to talk a little bit about this in a minute or two. So this is sufficient to earn the second and the third point right here in example 1. However, a bald answer does not earn the point. We need to see the mathematical setup. I'm sure you've heard that phrase before that leads to this answer. And here's an example of a decimal presentation error. This student does not earn the first point. They presented this interval incorrectly. It's a decimal presentation error. They don't earn the first point, but they do earn the second point for the definite integral. But the final answer here is not correct. I beg your pardon. They earn the second and the third point here. It is in this example down here in number 4, where they made a decimal presentation here. They earn the integral point, but probably what the student did is use these decimals in their calculator, and they have an incorrect value here of 105.93. So that's a 010. Wow. All right, the first point in Part D was for presenting the definite integral of v sub q from 0 to 2.8. So that means the student has to know that this definite integral was necessary as part of the expression for the position of the particle q. Now, again, the absolute value symbol isn't necessary here since v sub q is positive over this interval. So we want to see the student use v sub q of t with the correct limits. Now, unfortunately, there's another velocity function hanging around now in this problem. So we need to see the correct one. The student cannot misspell this. They can't use v of t here. Oops, I'm sorry. And if the student doesn't include a dt here, they may still earn the first point, depending again on our interpretation. In this example, the student earns the first point and is eligible for the second and the third. But in this example, the dt is missing, the integrand is ambiguous. So the student does not earn the first point. But they are still eligible for the second, but they cannot earn the third here. The second point in Part D was for presenting the position of the particle q. Simply stated, it has to be our answer. Here's some quick examples of student responses and how each was scored. In example 1, the student has the correct definite integral. They've computed the position correctly. They earned the first 2 points, and now they're eligible for the third. Remember, they still need to find that difference. In example 2, there's a decimal presentation error in this answer, this 45.94. So they earn the first point, they do not earn the second, but they are eligible for the third. And finally, the third point in Part D was for the answer, a positive difference between the positions of particles Q and P. And there was also an eligibility criteria here in this part. The student must earn the first point in Part D. Now, there was a special case here, but I'm not going to take the time to go into that. Any value may be imported from Part B. So in other words, if the student made an error in Part B, remember that trapezoidal sum part, they could import that problem and we would read with the student. And again, the difference may be implied. We really don't need to see a clear subtraction here. And finally, here are 2 more quick examples for Part D and how each was scored. In example 1, we see the definite integral and the position of the particle q explicitly stated. This student has reminded us of the position of particle p. Presumably, they brought that in from Part B. And the distance is given as an implied subtraction. I don't see the student actually write this value, 45.938 minus this one. If that's the correct answer, that earns all 3 points. And then finally, in example 2, the definite integral is presented, but there's still a decimal presentation error here. So this student earns the first point, does not earn the second, the first place of that decimal presentation error, but they have correctly done the subtraction. They earn the third point. That's a 101. All right, Michael, that's my best at a briefing. I'm going to do my best to pass this over to Vickie, if that's okay.
That'd be great.
All right, let's see.
And while you're doing that, just want to remind everyone that this is recorded, so you'll automatically receive a follow-up email in a couple days with a link to the recording. So don't feel free to write everything that Steve and Vickie are saying verbatim, word for word. Again, it's sometimes great with the recording. You can really go at your own pace.
All right. Sorry, Mike, I'm missing a screen here, I think.
Yep, I can toss that over to Vickie. Yeah.
Take care of that. Thank you very much.
No problem.
Thanks, Mike. Thank you.
Vickie, it's all yours.
Okay. All right, so we're going to look at the TI-84 first, and I am going to only concentrate on parts C and D because those were the 2 parts that the calculator was necessary, since the trapezoidal sum in Part B could have been left in that extended form. They didn't actually have to find the 0.75, although it would have been nice when they get to Part D and need to find the difference of the two values that they have. So in Part C, the students have the velocity of particle Q that is given. That's the second particle that was introduced, and it is that 45 square root of t cosine of 0.063 t squared. Now, I did take the liberty of putting this into my Y1 and my TI-84 ahead of time just to make this a little bit quicker. So you can go back and look at the recording instead of trying to follow along and try to enter it right this minute. So let me just explain what I think the students should probably do with this problem. So they need to find when this velocity on this interval from 0 to 4 for our time, the time interval when the velocity of the particle is at least 60 meters per hour. So I think it would be wise for the students to actually graph this. So let's, first of all, let's adjust our window. So I'm going to go to window, and I, again, have taken the liberty to adjust my window. So my x-axis is actually my t-axis. So I have my x-min at 0 and my x-max at 4. And my y is going to represent the velocities. So I played around with it a little bit, but I knew it had to be at least 60. So I thought, let's look at a window from negative 10 to 80 for my y's. I want to change my y scale here, so let me go down. I just don't want to see all those tick marks across the y-axis. So I'm going to make that 10. Then I'm going to graph this, and so we see our velocity function. If you recall, Steve mentioned that this velocity is always positive, which is really nice for the problem solvers, the students here. It doesn't make it quite as exciting as far as looking at the motion of the particle, but it'll still do. So what I would do is suggest that the students go back to their y equals window and graph y equals 60 as a horizontal line. And so let's graph this. And then they would need to find their points of intersection. And so let's go to our second trace, which is calculate. And we want to find an intersection. I'll press enter. So I have my first curve, and that would be the curve in color that is in blue. And then my second curve is the one in red, so the only two curves we actually have. And so then I want to do a guess. I'm pretty close to it, so let me just get a little bit closer there. And I'll hit enter, and there's my intersection. And so the students would need to record this to 3 decimal places. And then, of course, we have another intersection point. So we would go through this process again. So let's calculate. And we want an intersection. And so we want, let me move off this a little bit and make sure I'm selecting my first curve, my second curve. And now I want to find this point over here. I'm using my right arrow to move. I'm going to get fairly close to it, press enter, and there's my second intersection point. So the students would need to record those, and I would recommend they have stored more than 3 decimal places. So if you recall Steve talking about the errors in their approximation, they might have had some internal rounding problems, so they might not have recorded enough decimal places. And so if I go to my screen, and if you go to your grading standard that you have a link to later, you will see that when we put these on the grading standard, and Steve had it up earlier, we actually record more decimal places on the grading standard than the 3, so that helps a little bit. So let me quit this screen, and then we want to calculate. I'm going to go to Math, and I'm going to go to the numeric integration, which is number 9. So on our newer operating systems for the TI-84, we have a nice template, and so I would enter my lower bound, which is 1 point, And there are ways to store this. I just am not taking the time to do all of that at the moment because I really want to show you something on the TI-Nspire that is really nice. And so I go to my upper limit, 3.519, 174. And then what I am integrating, and again, we don't need the absolute value because as we have already stated several times, this velocity was positive. And so I'm going to go to my variables key, and I'm going to go to my y variables, and it was a function, and it was y1, and I like to put of x, and then I need to go and have my dx, and hit enter, and we have our approximation. And so that's pretty much what you would do with part C. The only thing that is different in part D would be that we need to add negative 90, and our limits on the integral would be 0 and 2.8 instead of these times that we have on the definite integral here. So I am going to now leave the TI-84 and go to the TI-Nspire, and it appears, there we go. So everybody see that okay? So it looks like I have already defined it. So one of the really nice things about the TI-Nspire is that I can actually define it in terms of t, and I elected to define it as the function VQ so that I could remember that I'm working with the velocity of the particle Q. And so what I would do now is go to a new window of the graphing. So I'll add graphs, and I've defined it. So now I can actually graph VQ of, I'm on the function graphing, so VQ of x. The bold VQ is simply a reminder that that function has been defined. And so I will press enter. I do not have a very good window, so let's see if we can remember the window we used earlier. So I will go to menu, and then go down to window zoom, and window settings. And let's see, we had 0 and 4. And auto would probably be okay, but I'll put a 1. And I think I did something like negative 10. And we want to go up to, I think it was, we could do negative 60 or whatever. We need to at least go up to 80. And I want to make a Y scale, which will be my tick marks on my Y-axis at 10. And so we enter, and so you see a graph that is very similar to the one that we had just a few minutes ago on the TI-84. I could press tab, so I'm sort of modeling the exact same thing that I did with the TI-84. So I'm going to go Y equals 60, and with the TI-Nspire, we would go to menu. I would use analyze graphs, although there are some other options that your students may be familiar with as to finding intersection points. So this one is actually modeling something very similar to the way the 84 looks. We'll go to intersection, except I just hit the wrong thing, excuse me. Clicked my mouse a few too many times there. So go back to analyze graphs. And I'm going to take the easy way out and type a 4. Notice that it doesn't ask me to select the graphs here because there are only 2 graphs, so it wants a lower bound, so that means I need to just be at an x value, which is actually a t value smaller than the intersection and then larger than the intersection. Now, unfortunately, with the TI-Nspire, we get a 2 decimal place answer. So hopefully you know that we can hover over that answer and press the plus sign and have more digits. Now the storing of this value is a little bit easier on the Nspire. So if I click on this and you see the store in blue right over the variables button, So control store, you can just click on the button. It will give you the option also, the variables button. I want to name it something other than the default VAR, so I might call it A since it would be on my lower bound. It, again, is bold, so that means it's stored. Likewise with the other point of intersection, so let's find it very quickly here. So we want to analyze graphs, and we want to find the intersection point. We need a lower bound, upper bound, hover over, although the hovering is not absolutely necessary, and additional decimal points on this screen. It is for the students to record the answers. So let's, so if you press, I'm sorry, I'm on the wrong thing. So if I click here and just press the variable button instead of the control variables, you'll see that you get the option to store. So I would probably name this one B, enter. Now it's going to be a very simple matter to come back to our calculator screen, and we want our definite integral. I'll access it through the template, although there are multiple ways to access your definite integral on the TI-Nspire. I'm going the wrong way. It's over here to the far right. And okay, I'm sorry, folks. I'm just clicking too many times. Enter. So the beauty of this is that I can type in the A for my lower bound. I like to use tab to navigate around these templates. B, tab, and since I have defined this, again, I can just put in VQ of T with respect to T, and I have an answer that is rounded, and this is one of the things that has if you do teach with the Nspire, that you definitely want to show your students, because there have been a few rounding issues with the default display that the students have. If they go up and highlight it and press enter, they will have more decimal places. If they perhaps need to record more or use more or make sure that they're rounding appropriately or something like that. Let's see, our time. I know Steve has some really cool other examples to show you, so I'm going to actually switch to a document where this has already been set up. So I'm going to go to this document. The students were not asked to, well, they were asked to find the position of the particle, but I decided that instead of just finding the position, I would actually define a new function that I'm now going to call the position of particle Q. So I defined it as xq of t. We know that it started at t equals 0 at the position of negative 90. So I'm going to have negative 90 plus the definite integral from 0 to t. So this is actually an accumulation function. Steve likes to call this the net area so far. Isn't that right, Steve?
Yeah, the area so far function.
Area so far function. And so I've actually defined it. So at this point, I could just put the 2.8 where t is. But the really neat thing is now that it's defined, I can go to a window, and that's not the window I want to be on. So I can go to a window. I've actually graphed parametric equations. So I graphed x1 of t as that xq of t, and I know it's supposed to be moving on the x-axis, but sometimes it's really hard to see the particle motion on the x-axis. So I just moved it up to y equals 1. So I graphed the second equation is y1 of t equals 1. Now, remember the particle had positive velocity, so it's only going to move to the right. Now, with the TI-Nspire, you might say, well, I didn't see you graph this, so I didn't see the particle moving. And you can do this on the TI-84. It's fairly slow, but you kind of do get a sense of the particle moving. So when we have our TI-Nspires, we kind of lost something that we don't exactly see the particle moving. But with the new TI-Nspire CX2, we have a new option. I'll show you this very quickly, and then let Steve go to his examples. If you go down to Trace, and of course we've got more menu items here, so click to the right. You will notice that there's now something called path plot, if I can talk. So I'm going to go down to path plot, and open it. And we are in parametric mode, so I'll go to parametric and hit enter, and we actually get like a play button. And you notice that here's our particle. That is, it's supposed to be at negative 90. It's kind of large, so I think it's just kind of off a little teeny bit. But if I start the animate, now what I should see is a particle moving only to the right. But if you recall from the graph that we had, that it was concave down, and it had a maximum. The velocity graph had a maximum, which means the velocity was positive or the velocity was increasing to the left of the maximum, so that means your acceleration is positive, and decreasing to the left. I can't get my right and left going here tonight. Decreasing to the right of the maximum, so that means your acceleration would be negative. So it's hard to see on this, but it's really fun to play with this with some other examples, and maybe some of Steve's other examples have something. So you get this little animate, and that's actually showing the motion of the particle from negative 90 to, let's see, what was it? We found position at 2.8. We didn't actually find the position at 4, but it's we could use that information that we had in Part C to maybe find it. But at any rate, this is sort of a nice demonstration that students can begin to understand a little bit more about what's happening with our particle motion. All right, Steve, I know you want to share those problems, so let me go back and assign you the share screen. I hope I did it the right way. We have too many options. Okay, Steve, I think.
Can you see my screen?
Not yet, Steve. I think you have to double check that you went to share my screen.
All right, here we go. Let's try that. How's that?
Looks good.
Okay, terrific. So I have 3 quick examples here that I'd like to show you, and these are part of TI and Focus, the set of videos that Tom, Vic, and I have been producing over the last 3 years associated with the AP Calculus exam. And this is from 2019, and the purpose here is to not only go through each of the problems, each of the pre-response questions in detail and show you how to solve them with technology, even if it's not a technology active question, but also to introduce a couple of other examples that are based on the concepts in the free response questions. These problems are generally very rich. As Vickie knows, when we're writing these problems, they often start out as maybe 20 or 30 points and have to be whittled down to only 9. So there's often a lot of information given in the problem that can lead to some other interesting problems, other interesting questions. So here's one. This one I called quick acceleration. And so we have the velocity of a particle moving along the x-axis is given by this differentiable function v, very similar to what was given in 82. So v is measured in meters per hour, t is measured in hours, and we have selected values of v in this table. You'll notice that this is a little bit bigger than the table given in the problem. And in part A, we want to show that there are at least 2 different times in that interval 0 to 4, so that the acceleration of the particle is exactly 20 meters per hour squared. Then we want to find a left Riemann sum and a right Riemann sum based on 5 subintervals used to approximate the value of that definite interval. And down in part C, we want to find a trapezoidal sum with subintervals as indicated in the table, very similar AP Calculus question lingo to approximate the value of that definite interval. And then, you know what, let's verify that equality. Let's make sure that the average, the arithmetic mean of the left and the right Riemann sums is indeed that trapezoidal sum. So that's kind of a cool problem. And again, this is part of TI and Focus 82 problem extensions that you can find on the TI website. I'm going to take a look at another one, Mike, if that's okay. So this example is based on the function v sub q that was given in the problem. And I've actually extended the interval for the velocity a little bit here. So we'll assume that this particle q moves along the x-axis, but this time for t between 0 and 9. So we want to first find some times t1 and t sub 2 for which the velocity is exactly 0, and then find the total distance traveled by the particle q during that interval. So this might be just a fuzz more complicated than the pre-response question. We want to find the absolute maximum velocity of the particle q over that interval 0 to 9, and in part C, find the absolute minimum velocity of the particle q over that interval. You might think about how to solve that problem or what the justification would be in that problem. And then when you find those two values, I want to find the distance traveled by the particle over that time interval, t max to t min. And then let's suppose that particle q starts out at the origin at time t equals 0. Let's see if we can find the maximum distance of the particle q from the origin over that time interval. That's kind of a cool problem. You can think about the particle moving along the x-axis, moving back and forth, and I want to find the maximum distance from the origin over that time interval. I would suggest you might be able to visualize this too kind of nicely with what Vickie just talked about on the TI-Nspire. And I have one more here. This is a brand new function, m, v sub m, associated with a particle that moves along the x-axis between 0 and 9. If you're following along with me, if you take a quick look at this function, this has a log in there, a natural log in there, a trigonometric function. So I hope there'll be no desire of any students to try to actually integrate this by hand. I want to find the maximum distance between the particle m and the particle q that was given back in example 2. Now, I'd also suggest that if you're really good with the TI-Nspire, and I think, Vickie, if I understand correctly, the TI-84 might be able to do this, but it would be a little bit slower. But this would also be a really neat problem to try to visualize, to see both particle m and particle q moving in the plane along an axis, along the x-axis, and somehow demonstrating visually, showing visually that maximum distance between them. That would be really cool.
That would be a fun problem to play with.
Wouldn't that be cool? Wouldn't that be cool? I'm sure you've already visualized how to do that. I'm not quite sure how I do it. I have an idea in Mathematica, but I'm not sure how to do it on the calculator. Well, thanks, Mike. Those are the 3 problems I've got, 3 extensions I've got. And I'll try to send this back over to you, or I've stopped sharing. If you can take the screen.
You got it.
All right, fantastic.
So thanks so much, Steve and Vickie. As we wrap things up tonight, if you have any last-minute questions for them, please try to get those asked. I know they'll do their best to get them answered. First thing I'd like to share is from our website, education.ti.com. If you move under the Professional Development tab and then slide down to Webinars in the middle, scroll down to Live T-Cubed Webinars. I might have mentioned it earlier, but this is tonight's part 1 in a 3-part series. So if you appreciated what maybe you saw tonight and you'd like some more, we're going to be having another part 2 of this webinar on February 18th, and another one coming up in March 17th. So you can visit our website and register for any or all of those upcoming webinars. Also available, I put the link in the chat window, but in case you didn't see it, the last portion of the webinar tonight that Steve was discussing some of those extensions he was getting from the TI-Nfocus, and those can also be found on our website under the Resources tab. In the middle is TI-Nfocus for AP Calculus. And again, here you can select a specific topic that you're looking to gain a little more information on, or maybe some additional resources to help you teach that topic. Or you can focus on a specific year that you'd like to look at the AP exam and the questions from that year. We're really excited that the T-Cubed International Conference is coming to Dallas. It's now coming up pretty quick, just a couple months away, this coming March. It's a great place to interact with like-minded educators to gain additional insight into content, pedagogy, technology, or any combination of those. So if you'd like to learn more about the T-Cubed International Conference, please visit our website, education.ti.com. More information can be found there. Also, we said that earlier that tonight we're giving away to one lucky winner a registration for the T-Cubed International Conference, and tonight's lucky winner is Isaiah Tapia. So Isaiah, congratulations. We'll be in touch over email in the next couple of days to give you a little more information, but we hope to see Isaiah as well as everyone else at the T-Cubed International Conference. And to get us ready, we're going to be doing a slow chat book study on Twitter over the next coming weeks. It's going to start January 20th. The book we're going to be reading is called Blind Spot, Hidden Biases of Good People. And the way this works is we'll read basically a chapter a week, and on Twitter you can kind of add your comments and questions and thoughts. So feel free to pick up the Blind Spot book and, again, start joining us on January 20th on Twitter. More information will be coming soon. When you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback guides us as we plan future online events, and we really hope to share your thoughts in the post-webinar survey. To receive a certificate of attendance, go ahead and click the link in the chat window. Also, there's a link for the documents that I used tonight. If you happen to miss these links for any reason, check your email in a couple days, and you'll automatically get links to the certificate, the documents, and to the recording. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. Lastly, if you're in need of any post-webinar follow-up, feel free to give us a call at 1-800-TI-CARES or send us an email at ti-cares@ti.com. We'd love to hear from you. Thanks so much, Vickie and Steve, for everything you shared tonight. It was great.
Thanks, Mike.
Thanks, Mike. Enjoyed presenting with both of you.
Thanks so much, and we hope to see everyone back online next week. Have a great night.